Alright, hi everyone, welcome back to our C++ programming course on Friday, and this is our fifth lecture actually. Alright, so what are we going to talk about today? Today we will cover basically two important topics. I mean, the second topic is much more important than the first one, but nevertheless, so two important topics. The first one really is operator overloading. So today you will learn what operator overloading actually is and how it can be used and what you can do with it essentially. You already used it a bunch of times, for instance, for your cout stream, which is a special global variable, and there you use the left shift operator to basically write some data to the character output stream. In addition, we had the standard string, and we used the standard string, and did we actually have an example on that? I'm not quite sure, but anyhow, the operator plus, for instance, is implemented for strings, as we will learn in today's lecture. And so you can use some shortcuts. So basically, operators can be considered as shortcuts to ordinary function calls. Then in the second part, in the larger part of this lecture, we will discuss about memory, the different kinds of memory that your computer program comprises of when run on an operating system. And also we will discuss about dynamic memory allocation, which we have not yet really used, or if we used it, we used it implicitly, as you will learn today. And then we have to discuss two very important special member functions, namely the copy constructor and the copy assignment operator. And also we have to discuss about the move constructor and move assignment operator. And those will be of importance when you're dealing with dynamic memory allocation yourself. Then you cannot just stick to the default, then you really have to find a good implementation yourself. And at the very end, I will give you some notes and some hints on how to use dynamic memory allocation effectively, and how to use it effectively. And maybe also some cases I will give you some examples where probably not to use dynamic memory allocation. Okay, but let's go through this little by little. So operators, those are some example operators, and in C++, if you wish to specify that you are talking about an operator when you wish to provide an implementation for that operator, you always have to prefix the operator that you're talking about, so to say, with the operator keyword. So operator is really a keyword. And for instance, here this single equal sign, which is in computer programming most of the time, is the assignment operator, and also in C++, this is the assignment operator. And if you wish to talk about the assignment operator, you have to put operator as a prefix, so operator equals, so this is the assignment operator then. And the same, of course, also for plus, minus, multiplication, division, and all the good stuff. So you always prefix with operator, the operator keyword. And of course, this is only a limited number of operators, but there are lots and lots of other operators that you may wish to use and also may wish to overload. And a complete list I will refer to on one of the next slides. So how does it all work with operator overloading? So operators have a certain meaning which is associated with them. In general, you could also always replace an operator by a function. So an operator is basically just a shortcut for a function. That's the first thing to keep in mind. And then here, for instance, we have an example. We have an expression on the right-hand side of the assignment statement where we just have the operator plus, and then we have two integer literals, one of the left-hand side and one of the right-hand side. And we add them up together, so this is the mathematical addition. And then whatever the result is, in this case would be 9, we assign to the integer variable sum. So plus in this case is the mathematical plus that sums up two numbers. But you can also overload this operator plus, or any operator really, or almost any operator. And an overloaded operator may has more than one meaning. For instance, we will see on the next few slides that you can also overload the operator plus for strings. So the operator plus really has multiple meanings. And now the question is, how does the compiler know what meaning it should use for that operator plus? And this can be done by context. So the meaning of an operator depends on the context, and the context is almost always the type or types it is applied to. So you can, for instance, have a unary operator which only takes one argument really, and then the type it is applied to gives the meaning to that operator. And if you have a binary operator like operator plus, then the types on the left hand and right hand side dictate basically the meaning of the operator plus. For instance, in the above, if you use the operator plus with two integers, then the built-in operator plus from the programming language itself is applied, which basically sums up the two integer literals. And for instance, if you use operator plus and you have on the left hand and right hand side some std string variable, then the operator plus for the string variables is used. So it's a different operator plus, but it's the same symbol. And again, the meaning of that operator now depends on the context. So overloading operators is a powerful instrument because you can write quite some neat code if you have that, if you can do that in the language, because you can really implement algorithms and write code like shown in math textbooks. This is particularly true if you have to implement some stuff from the domain of mathematics in general. That is, computer graphics applications are mainly really written in C++, and then you can define yourself some linear algebra types, and really you can have vector times vector, vector plus vector, vector times matrix, and you can really build your whole world of linear algebra from mathematics in the C++ language. And so computer graphics would be one excellent example of why that might be useful. So you can really write code which looks like you would write in your math textbooks. Have you ever used an overloaded operator? Question to you, and the answer is of course yes, you already did that. If you remember the cout streaming variable, which is some global special variable in IOStream, in the IOStream header file, and then you use the left shift operator. And also for string, you used operator plus for strings, and you also used probably, at least I had it on some of the previous slides, where we used plus equals for strings, which just takes whatever contents is in that string variable, and it in addition appends whatever is on the right hand side to that string variable. Again, here's an example. So you have two strings, a plus b, and it basically just concatenates both of those strings. So the result will contain 4 a's and followed by 3 b's. That will be the contents of the result string, so to say. One should be careful though. So overload operators should be thoroughly designed. Why is that? Because they should behave as expected. Why is that? Because an operator has no real name. I mean, an operator is just a symbol, really, for the most parts. And if you implement a function, you can give that function a meaningful name, right? So, I mean, you can give a function an arbitrary name, which describes really what it does, and then someone can use it. But for an operator, I mean, you just have, usually you just have one symbol, and then the meaning must immediately be clear to the writer of the code, first of all, and also at some point for the reader of the code that you're writing. Maybe a colleague writes, you write some code, and your colleague wishes to use parts of your code, then he also needs to understand what your code does and eventually also how it works. So please implement the operators as such that they act as expected. So you could also do that funny thing, and I advise you please don't do it. You could do the following. You could have again two strings a and b, and you can overload the operator plus on strings or for strings to delete the contents of a and b and fill the result with "I'm a very funny guy." We should do that for obvious reasons, and I also would not recommend to do that in a corporate environment. You'll probably lose your job if you do some strange stuff like that. That's not funny, and that can cause, of course, a huge amounts of damage. But it's funny though. But nevertheless, don't do it. So now back to the question: what operators can you actually overload? So you can go to CPP reference and search for operator overloading. And here it tells you, you can really overload any of the following 38 operators. So that gives you plenty of room for custom operators that you can implement, such that you can use them really as shorthands for, rather than a function, you can use an operator as a shortcut. So if you write a data type, if you implement yourself a known data type, then please only really overload operators that are useful and also whose meaning are clear, whose meaning is clear, sorry, and do not overload all operators or as much as possible. So it's not cool to overload operators. You can do it as a shorthand if the meaning is clear and precise, but I mean you don't really have to overload everything that's possible, and usually that doesn't make any sense at all. From some colleagues who work in computer graphics, I know for a fact that they overload some operators like the modulo operator right here. I mean, it's pretty small, but I hope you can read it anyway. The modulo operator is in computer graphics sometimes overloaded as a vectors cross product, which I really find hard to understand. So you can do it, sure, but again, I mean, this would be one of those cases where I say personally, the meaning is no longer clear and unique, so you probably shouldn't do it. How about custom operators? Like in Python, for instance, there's this operator times, which is basically the power, implements the power function. So the power operator. And this of course would also be possible in C++. It's no problem at all to allow for custom operators. But again, I mean, this times operator is really hard to understand what it should do. I mean, once you know it, it's probably clear. But C++ does not have that operator because for the reason as stated in the above. Although, of course, arbitrarily defined operators would be possible. It's easy to integrate. But again, not intuitive. I guess by now you got the point. So let's have a look at the operator left shift for the streaming cout variable. So some operators are kind of member function like. So some operators can be or must be a member of a certain type that you're about to define. And then there are some other operators, mostly binary operators really, which can be defined inside a type or outside a type. So, I mean, semantically, it all means the same. It's just a matter of personal preference. I guess I already told you on one of the last slides in the last lecture, that the output stream operator is, of course, not a member function. It's a binary operator which can be used to write a certain type to the character output stream. And if you really wish to define it inside of a type, you have to use that friend keyword. So that's what I already told you. And now let's have a look on a concrete example. So what you could do is you could define yourself a type using the keyword struct, of course, and your type can have two member variables, I and D, and you give that thing a constructor which receives two arguments, an integer I and a double D, and you fill in the internal I and D with the I and D of the parameter list using the constructor initializer list. And other than initializing all its members, the constructor doesn't do anything in our case. And then you can, of course, create a variable t of type, and you give it the desired arguments here such that the constructor can do its work. It will allocate some memory on the stack and it will initialize all the member variables. And now sometimes you are confronted with this situation where you would like to print the contents of a variable of that type to the character output stream, for instance. And for that thing, you need to, to happen here, you need to implement the operator left shift here for the output stream. So you can have it as follows. So this is a binary operator, and on the left-hand side of the left shift operator is the output stream you wish to write to. And you already see it here, that's the cout variable in this case. And on the right hand side of that thingy here, you have a t. And a t is a variable which you receive within this operator implementation as a const ref type. And then you can implement the operator and do some stuff. So basically you shove in the individual data members of the type into the output stream, and then you just return the output stream. And because you've defined that output stream operator, that left shift operator within the type definition, and it's not a member function, you have to use the keyword friend here. Otherwise it won't work and the compiler will give you some strange error message, if I recall correctly. I mean, you will in any way you will get some error message. And you can also define such operator outside. So that means you can define your struct type. Same definition here, really. And then you have your output stream operator. And here, in this case, it has not. It doesn't need to be declared friend because it's not part of the type. But rather it's I don't know, external. I mean, at least its definition is outside the type's definition. So it's both alternatives that you can use. My personal preference is to define it inside your type, such that you have all the definitions that can be used on that type that you are about to define, in this case type, such that all definitions are together and come together with that type. Otherwise, it is sometimes a bit confusing to see what operators are really overloaded for that type. So I'm a fan of defining such things inside the type definition, but you can do as you like. I mean, the compiler couldn't care less as long as you have some definition within your program. The program will run happily on your machine. So maybe let's have a more useful example. Let's have some more examples on operator overloading. So please remember our vec3 type from the, I guess, previous lecture, if I recall correctly. So we had a class vec3 which internally stores three double variables, x, y, and z, and they are private, so that means you cannot simply access them from the outside. So remember, separation of data and interface. So hopefully, probably we will have some good public interface which we can use to interact with those pieces of data. And oh, surprise, we do have that. So we have two public constructors. So one kind of default constructor which takes no arguments, and if that constructor is used, all member variables are initialized to 0. In addition, we have a second constructor which takes 3 double arguments, and it uses the 3 double arguments from its argument list to initialize the data members here, x, y, and z. And please observe that you can use the same symbol name for the parameter list and for the data member names, variable names. And so the compiler is smart enough to figure out what you wish to do. So you want to take this x from the parameter list to initialize this x, which is basically the data member x here. Then we had some size function which returns the number of elements of that vector, 3 in this case. What else? And we had the Euclidean length function, that's good. And we also had the left shift operator here, which just takes the individual double variables x, y, z and shoves them all in the output stream variable os, and which is eventually returned from that operator implementation here. Why is operator left shift declared as a friend? Again, because we are defining it in the type definition here. If we would define it externally or outside the types definition, we would not need to use friend here really. All right. All right. And now we can do the following. Really, we can construct a vector variable of type vec3. Use the second constructor to initialize its member variables with 4, 5, and 6, and then we can use the left shift to print it to the command line. So far, so good. Maybe let's overload some more operators. Let's overload operator plus and also operator squared brackets for convenience, such that the type can be used more effectively. This is all the same as on the last slide, and now here that's new. So we overload the squared bracket operator here. The squared bracket operator is usually an operator that can be used to access some data within a type. And we define it as follows. We define the squared brackets operator here to receive an index of type size t. So size t, please remember, it's some type alias to unsigned long or something like that, if I recall correctly. So at least it's an unsigned type, which makes sense for an index to be used, because the negative indices don't make any sense here in this scenario. So and then we have a nice switch, and depending on the index, if the index is 0, we just return x, the member variable x, and then we break and done basically. If the index is 1, we return y, and if the index is 2, we return z, and then we break after each thingy. And if the index is something else other than 0 to 2, because we only have 3 member variables, really, it only makes sense to have 3 valid indices, and probably we wish to start at 0, because that's what programmers expect. And therefore, we use 0 to 2 as valid indices. And if we observe another index here, which doesn't make any sense, we just return none, which is a special value, not a number, to indicate not a number, which you can check for. And also observe that we return a reference to a double. So that means if you use the squared brackets operator on a variable of the type vec3, we will return a reference, which we can also then modify, of course. So we can, for instance, say, yeah, a vec3 variable v at the position 0, and then we write 42 in it, and that would actually write 42 in the member variable x, because here we're returning a reference to that member variable x. And remember, if you do some modifications to a reference, it actually does this modification to the underlying type, memory, variable, whatever you wish to call it. Also, let's overload operator plus, and here we overload operator plus to perform a component-wise addition, really. So we receive two arguments here. So one vec3 LHS, which we pass by value, so not by reference, by value, which means the left-hand side is copied into that function, because default, if you do not specify otherwise, passing into a function or also into an operator is pass by value, which means we copy that thing into that function or operator in this case. And the right-hand side we pass as a const reference. And why is that? When we copy one thing, maybe for instance the left-hand side, into that thing, we can directly use it for our result, so to say. So we can now iterate the left-hand side, all the entries of the left-hand side vector, and just add the right-hand side's entry to the corresponding left-hand side's entry, both at position I really, and I iterates from 0 to LHS.size, which is 3, of course. And then we return the result, and yeah, we have a result which is basically contains the entry-wise sums. Also note that here this squared brackets operator only works because we just defined it here to the left-hand side. So basically by using the by implementing the squared brackets operator here to be used with an index here, we can use this for loop here to implement that, to make it work. That's the idea. And then we can also overload the standard left shift operator. We already did that on the last slide. So what we can also do, besides using the squared brackets operator here in the for loop, we can also have a vec3 variable v. And we can say, yeah, I mean, this uses the default constructor. So essentially all member variables are initialized to 0. Then we say, yeah, v at the position 1 should be, we wish to write the integer literal 12 to it, which means that y is set to 12 after the statement. And what else? We can also have a const vector, of course, a const vec3 variable w. And now all of a sudden the squared brackets operator does not work anymore. Why is that? The vector variable w is const, and the problem is that the squared brackets operator here returns a non-const double ref, which means if you would be able to use that operator here, you would be able to change the contents of w. However, this is not allowed because you declared it to be a const variable. So at this point, the compiler will complain, and the compiler will say, oh, I have no const version of that squared brackets operator. And that means we really need a const version of the squared brackets operator, which we implement as follows. So the internal implementation is really exactly the same. But first of all, after the parameter list, we use the keyword const to denote this operator. It could also be a member function, which you declare const after the parameter list. But this const here means that this operator or member function in general does not modify any of the internal data, meaning any of x, y, z. So if a user uses this operator or a member function declared const, then this member function does not modify the state of the object, and therefore it can be safely applied to a const variable. And also, please observe that we are returning a const reference here, and the const reference cannot be changed outside. You can only read from const ref, but you cannot really write through const ref, because that's the purpose of const ref. And so in this case, where you apply the squared brackets operator on the variable w, because it's a const vec3 variable, the const version of that operator would be applied and would be called. All right. Yeah, and I already told you that. So a const Const function member or operator is one that does not modify the data members. So now we can use the following thing. We can use vec3, the vec3 type to construct two variables, and we can also use the square bracket operator here, and then we can also add them up. So v1 plus v2, and the vec3 will contain the entry-wise sums. And then we can print the result to the command line, and it will output 5, 52, and 9 as a result. So by now you should be able to operate the following operators yourself. So you can now go ahead and overload operator minus, so maybe to compute the component-wise subtraction. So here you could also overload operator times or operator multiplication between two vectors, and it returns a double. So probably, I mean, from mathematics, you would overload the times operator here between two vectors as a scalar product. This is also why it returns a double. So this would usually be the scalar product. You could also have another operator times, and which you overload in case you have on the left hand side a vec3 type and on the right hand side a double type. And then you could basically just scale that vector up, and you could multiply each entry of that vector LHS with the double on the right hand side here. And then basically you can, in mathematics, you would make your vector longer or shorter, depending on that factor here, RHS. Yeah, here also, I mean, in computer graphics already told you that this sometimes implemented as cross product, vector product, but yeah, not very intuitive. I wouldn't do that. And also you can overload all the comparison operators here, which is quite handy oftentimes. And please also observe for the comparison operators here, and also equals and not equals, you only really need to implement operator smaller than and operator equals. That's important to note, because once you have operator smaller and operator equal, you can express all the other operators basically by just using the smaller than operator and the equal operator or equal to operator. So because I mean, how would you do how would you implement the not equal operator? You would just call operator equal, and then whatever is the outcome you would negate, and then you have not equal, so to say. And the same game pretty much for that operator smaller than. But also please keep in mind, here we are dealing with doubles, and I'm not quite sure how you would implement the equality operators to make sense and mean such that they are meaningful. But besides that, please be very careful. It does not make too much sense in computer programming to check two double values for equality, because recall that double data type or any floating point data type really is only an approximation of mathematics. And also, if you use doubles or any floating point types in computations, you get rounding errors, because the machine can only store that many bytes for a certain floating point value. That means you encounter rounding errors, and therefore it really does not make any sense to compare two double or floating point variables for equality, because they will not be equal. They might be very close, but usually they are never equal. So one floating point number can be smaller or greater than the other, but just a hint, do not check for equality, it doesn't make sense. Yeah. How about custom operators? So can you define your own custom operators? And I already told you, no, that's not possible in the language itself. So in C++, that's not allowed, because semantics and meaning, it's hard to guess the meaning of custom operators. But you can nevertheless, within the language, not built in, but within the language, you can use some ugly hack to allow for custom operators pretty much. That's nothing, again, you should do in any software product that you wish to use for production. I mean, later on, one of the last lectures, we will do some kind of fun lecture where I will show you and tell you about all those nasty hacks, and I will show you how that can be done, and also some similar neat tricks. But it's more fun than of any use, of course. But I mean, you can show your colleagues and you can show off a bit how good you know C++ programming, how good you know the C++ programming language. Okay, so that would be pretty much it on operator overloading. If you need to do it, just look up the corresponding operators, and now you should have a good idea how to implement those operators. Yeah, now, before we continue on dynamic memory, we need some more special pointer. We need to discuss the so-called this pointer, which is some kind of special pointer. So if you go to cppreference.com and you look for the this pointer, it will tell you the keyword this is a PR value expression. At this point, you don't need to know what a PR value expression is, but what follows again is important here. The keyword this is an expression whose value is the address of the implicit object parameter, object on which the non-static member function is being called. It can appear in the following contexts: within the body of any non-static member function, including member initializer list; within the declaration of a non-static member function anywhere after the optional CV qualifier sequence, including dynamic blah blah blah, that's not that important, and within default member initializer. All right, what does it mean? So if you translate, if you boil that down, really it is this pointer lets you access the address of the object on which a member function is being called on, also known as the address of the receiver object. So again, what does it mean? So imagine you have a vector vec3. You have a vector vec3 variable v, and that v variable has that vec3 type has a member function size, which returns 3 because vec3 has 3 entries. Then you are allowed to use this keyword to access the pointer, the address of the variable the member function size is being called on. And what you would write in code is a v.size to call the member function size on the variable v, and v is the so-called receiver object from which you can obtain the address by using this pointer. That might be useful for the current exercise sheet. I mean, if I recall correctly, for one or for both of the assignment operators, so copy and move assignment, which you need to implement this time, you need this pointer, or you may wish to use this pointer. We will have in a different lecture later on, we will have all the details on this pointer. For now, hopefully you have a rough idea what it is. Maybe again in simple words, so this pointer gives you the address of the object a member function is being called on. And sometimes that's very useful. You need that functionality. Okay, that's a quick detour on this pointer. Now, before we come to dynamic memory allocation, let's talk about memory layout in general, such that you have a good feeling on why we need dynamic memory allocation and what's its use and all that good stuff. So if you go on the internet and you, I don't know, Google or use your other favorite search engine, if you go and look for memory layout in Linux systems for C++ programs, you will find the following memory layout. So if you write a program and compile it, and eventually you run that program, the compiled binary program, on your operating system of choice. At least I can comment on Linux systems here, and also for Mac OS it's the same game. On Windows machines I have no clue. But if you run your program on your operating system, your program has the following memory layout. So, and this holds for each program that you run. So a program resides in your computer's main memory and of course is executed, and it has, I mean, the outer box basically is the memory of your program. And this memory, this piece of memory, is again divided in so-called sections of different kinds of memory, which we now discuss here in more detail. And usually you have high addresses above the kernel as a memory segment, and low addresses here at the text segment of the memory. So what's the kernel section used for of your memory, where your program lives really? So in the kernel section it contains the command line arguments. So if you write a main function, you can use the signature where you have an integer argc as a first argument, and as a second argument a character pointer argv, and when you call your program, your operating system will put all the command line arguments that you are calling your program with into that section of memory here. And also it will contain the environment variables. So in, I don't know if you need to know that, but probably you already know if you're familiar with Linux. You can also have some environment variables which you can read from your program. Then you have stack memory, which is very important. So stack memory contains function parameters and functions return addresses. So whenever you call a function, a new stack frame is put onto a new stack frame is basically put into the stack segment of your computer memory, and then the function parameters are in there. Also local variables are on that stack memory, and if you exit from that function, if you return from that function you just called, the stack memory is automatically cleaned up. So all local variables are basically removed from the stack, and then you can call another function, and so on and so on. And the stack usually grows downwards. So when you call lots and lots of functions without returning, maybe you have a deep call chain, your stack will grow and grow and grow and grow until at some point you hit a return, and you return and you return, and then you go back up and get rid of the last stack elements. Yeah, and stack because it's implemented as a stack, so which means first in, last out, following the first in, last out principle. Okay, but stack memory alone is not sufficient. Sometimes you need what's called a heap memory, and heap memory is a special section of memory which grows upwards, so into the stack, or hopefully not into the stack, but in the direction of the stack. And this is called heap memory. And heap memory allows for allocation of huge chunks of memory. If you need to store lots and lots of data, you probably wish to put that on the heap. Yeah? So what you need to know is the heap memory allows for allocation of huge chunks of memory, whereas the stack memory is usually limited by the operating system. So stack memory usually limited in size by the operating system, and if you have large stuff you can put it on the heap, and heap is also oftentimes called the free store, because you can just take and give what you need. You can ask the operating system, hey, please give me 2 gigabytes of memory, of main memory, and then you can do whatever you wish to do with that 2 gigabytes of main memory. So then we have the data section, which contains the global variables. So initialized and uninitialized global variables are in the data section of the memory. And then at last you have a text section, which is also read-only. So the text section is read-only, and it contains your program text, which is, this is also why it's called text, so program text. And basically that's the machine instructions, so your program instructions that need to be executed. And for each program run, if you compile your program into a binary and then you run your binary on the operating system of choice, this is what you get for each program run. So for each program run, it has a chunk of memory for its own purposes, and then this chunk of memory is divided up into different segments, and the different segments are used for different things, which are listed here. So, and I mean, in general, it's nothing to be afraid of. I mean, memory is just a linear piece of addressable locations where you could, where you can write some data in and read some data from. So this would basically just be one string of bytes on your machine. Of course, this has been somehow simplified. If you wish to learn about all the details on the different segments and why we have those different segments, please go to this web page here. So I put the link on the slide here, and it has really a great explanation on all the different segments. But unfortunately, we ourselves here don't have the time, because now we, in a few seconds or minutes, we need to discuss dynamic memory allocation. And again, C++ is huge. For all of the details, please refer to the references here. Also, maybe please read that page at home. It's not too long, but you have to take, I don't know, 15-20 minutes, which we don't have here within the lecture. So I highly encourage you to read this page. So why do we need dynamic memory allocation? So we now know that on the heap we can put huge amount of stuff. We can allocate all the memory essentially, and then we can make good use of that, hopefully. So consider local memories, local variables of fixed size, so to say. So if you would go ahead and within a function, you would write the following. So I would like to have an integer array, which can be accessed by the variable's name buffer. And the integer array should store 10 integers. So this is basically local memory. And this goes on the stack. But then we have one problem here. What happens if I need to store more than 10 elements? Again, stack memory is limited by the operating system. That's not very good. And also even worse, what happens if you don't know the number of elements that you need up front? So maybe you have a program that computes some meaningful things, and you ask the user for input. Hey user, please, what should I compute? And then the user types in, I don't know, some crazy number. And then, I don't know, you say you need to, you need 1 million integers. And as the user types it in dynamically, you don't know upfront. So you need to allocate memory dynamically. Yeah, because you cannot just type in your program code, I would like to have 10 integers, because sometimes you don't know upfront. And then, you really need to make that a dynamic choice, really. What happens if you need to store 1 million elements? Also, that probably won't fit on the stack, because the stack again is limited in size. Why is that? Why is the stack limited in size by the operating system? Please think about deallocation. So at some point the memory has to be cleaned up, or has to be freed at some point to make space for other important stuff that you need to store within your program. And also, I told you that if you call a function, then everything within that function, local variables, function parameters, the return address where that function needs to return once it has finished, so to say. Everything is put onto the stack. And now if you call a few dozens of functions without returning, so your stack grows and grows and grows, and if each function, or maybe let's the other way around, because the stack is first in, last out, if in the first function call you allocate 1 million integers, which is a huge number of bytes that you need, you have a huge stack. Your stack grows in size very fast, and then you have a bunch of other function calls down below, yeah, which are also on the stack. And until you return from all those functions to the function which allocated your 1 million integers, you cannot really free those 1 million integers, because you have different functions which are still on the stack. Yeah? So you cannot just free, and then you run out of memory very quickly. So I mean that's hard to grasp and to understand, but maybe at the end of this lecture, please think about that again and one more time, and it hopefully makes a click, and then you know why that is. Okay, also what if data should be used in more than one scope? So a local variable, so a variable defined within a function, is only valid within that function. So but what happens if you need some data that is valid across multiple functions? Sure, you could make it a global variable, but again, global variable is in memory for the complete program's lifetime, and it just costs huge amount of space, really. And also globals are bad because they break local reasoning, and yeah, it's problematic to say the least. But now the dynamically allocated heap data solves the problem. Why is that? So what you do on the heap memory is, this is this section of the memory, as I already told you. You simply take, or it's called then allocation, you allocate memory, what you need. So if you need 1 million integers, you allocate 1 million integers, and if you don't need them anymore, you say, yeah, please get rid of that, and by magic, the operating system gets rid of that. And you can really allocate chunks as large as your RAM chips in your machine. So you can, huge amounts of bytes you can allocate on the heap. But caution, once you allocate memory, you're basically asking your operating system, hey operating system, please give me, I don't know, let's say 2 gigabytes of RAM. And then you can perform some computations with that memory, within that memory. And if you don't need it anymore, you have to free that memory yourself. So basically, once you're done with your computation, you have to tell your operating system again, hey, operating system, thanks for providing me those 2 gigabytes of main memory. I no longer need this memory here. Please free it and maybe give it to someone else who needs it more than I do. So you need to do the cleanup yourself. And this is kind of tricky. In languages like Java, you have something which is called a garbage collector, which also automatically figures out when you do no longer need a piece of memory. It's freed automatically, but C++ and also C do not have that. So C and C++ are not garbage collected languages, so they don't have a garbage collector. That means you have to do the cleanup yourself. So that means free the memory after you used it. And also the memory is yours until you explicitly free it. There is no out of scope, so the memory exists and is reserved for you as long as you tell the operating system otherwise. And also, please do not lose the memory handle, because if you ask the operating system for memory, you get memory, and your heap grows upwards towards the stack segment. But if while you're computing stuff, if you lose your memory handle to that piece of memory, you cannot free it anymore. So better do not lose your memory handle, very important. the keyword for allocation is new, and the keyword for deallocation is delete. So we will have some examples now on how it all works in detail. So, but for now, please remember pointers. So what we could have is ordinary integer variables I, which is a value type, and we assign 42 to it. We could also have pointers, pointer typed variables. So we have a pointer to an integer variable, which goes by the name of IPTR. And we let this pointer variable point to the address of I. So this thingy here points to I. And this was this ampersand here is the get address of operator. So get the address of I and store it into that pointer variable. Pointers now become very useful, or to put it in other words, if we would have no pointers, we couldn't use dynamic memory allocation. So they're inevitable. And operator new allocates the amount of memory that you need. But the problem here really is that operator new cannot provide a name for your allocated memory. So it cannot just make up variables names. And therefore, the only way really to communicate with the memory that you get from the heap is pointers. So the operating system will allocate some memory for you and will give you not a variable name, because again, it cannot just make up variable names for you. And therefore, it just gives you the address where that piece of memory that it has allocated for you sits. And then you can use it via the address. So again, it simply returns a pointer, or aka address, to your memory. And once again, caution, please do not lose size information. Otherwise, you risk undefined reads and writes. So if you allocate, let's say, 1 million integers, you better also somewhere store that you allocated 1 million integers. Otherwise, if you need to iterate that memory using for loops or whatnot, you're screwed, basically. Also, what's important to note is do not forget to delete, otherwise you leak memory. If you forget to free that memory after you used it, I mean, you can do it once and it may work perfectly fine, although your program still comprises a memory leak. But imagine you have a long-running server application, and now also imagine that you do some heap allocations within loops. So I don't know, for every user that logs into your system, you allocate some stuff on the heap and all the good stuff. But if you never free it, you will at some point run out of memory, and then your program will crash, and your operating system will kill your process and your program. So please also delete memory that you no longer need. And also, to make things worse, you are not allowed to delete twice. So if you have a pointer to some memory that you allocated, and then you did some cool computation, cool stuff with that, and then you delete it, perfectly fine. But then by accident, maybe you delete it a second time. I don't know, happens, believe me, that happens. This is called a double free, and this is also prohibited. I mean, that's undefined behavior immediately. So do not forget to delete the memory, but also do not delete twice. Otherwise, you leak memory, or your program also has undefined behavior, and hopefully it crashes. It just crashes. That would be the best case. Otherwise, it may continue to run, but then does some stupid things and doesn't do its work anymore. By the way, a great and funny talk about undefined behavior, that's just a toy talk. I mean, there's no real contents, but it shows you all the magic of undefined behavior in C++. And also it might cause nightmares. So if you would like to have some fun, you can watch this talk here. It's only like 15 minutes or so. Yeah, it's quite fun. Yeah, and then after having seen this talk, you either hate the C++ programming language or you love it. Depends on your mental health, I guess. All right. Allocate and deallocate memory, and delete, deallocate, delete. It's same different wording, but the same semantics. So the keyword for allocation is new, and in fact, new is not only a keyword. New is an operator that you can even overload. So you can theoretically overload the new operator, which you probably shouldn't do unless you really know what you're doing. Otherwise, please don't. So the standard signatures are the following. You can have ordinary new, so operator new. It receives a size t, so a number of bytes it should allocate. And if it has successfully allocated that amount of bytes, it will return a pointer to you. And it will return a void pointer to you. And void is some magic type, which means void is no type or any type. So that means it's just a pointer to memory. I don't have type information here. This you would do for objects if you need to allocate individual objects. If you need to allocate arrays, then you would use the square brackets new. So new square brackets is the array new. It's called array new because you use it to allocate arrays. And also it receives the number of bytes that you wish to allocate as a parameter, and it also returns a pointer to that allocated piece of memory. Yeah, already mentioned that. If memory cannot be allocated, new can also throw an exception. We will learn what exceptions are in the next lecture, I guess. It's basically a way to indicate an error. And the exception name is bad alloc. This is thrown if the new operator couldn't allocate memory. When can that happen? That can happen if you allocate a huge amount of memory, which is more than your machine currently has to provide as free memory. If you allocate more than you have, then obviously the allocation cannot take place because there is just not that amount of memory available, and then a bad alloc exception is thrown, which you can also check for. But in practice, in reality, no one really does that, which is quite sad. The keyword for deallocation is delete. Delete is also in fact an operator, which also can be overloaded, and the standard signatures are standard delete for objects and array delete for arrays. And delete, the operator, doesn't return anything, and as a parameter it receives a void pointer. So you give it a pointer, you give it the address of that memory that is yours, and then it will just get rid of that memory and tell the operating system, here, I don't need that memory, use it for something else. Again, recall that every new needs a delete, otherwise your program contains a leak or undefined behavior. Okay, so those are the operators here. A question one can ask is, why is there a distinction between plain objects and arrays? I don't know, and the answer, the honest answer is, it's just a syntactic oddity. So this really has no use at all, absolutely no use. It has just been introduced, and then people thought it was good, and they just stick to it. But I mean, it has really no use at all. You could have, oh, pardon. It also would have all worked out if you just have a plain new and plain delete. But anyhow, to make matters worse, please do not confuse between the array new and array delete, and ordinary new and ordinary delete. Please do not allocate with the operator new and then free with the array delete, or the other way around, vice versa. If you do so, again, you have undefined behavior, which you probably do not wish to have in your program. All right. A note on double free. So maybe let's give ourselves the task to allocate a single integer variable on the heap. So now we don't wish to allocate an an integer variable on the stack as a local variable, but rather we wish to allocate it on the heap, on the free space. That's also possible, of course. So how does it work? We tell basically the program, hey, I would like a new integer. So this one tells basically, yeah, please give me an integer which you allocate on the heap. And initialize it to 13. So this is basically just the integer constructor. And yeah, as it cannot provide a name for that, it just gives you the address, and we store the address in a pointer to an integer variable, dynamic int. And dynamic int is a pointer which now stores the address of that piece of memory that we allocated on the heap. And now by dereferencing this pointer variable, we can now write some data within that piece of memory which has been allocated here. So we can now write 42, and somewhere on your heap you have 42 in a memory cell. You can also print the contents, and because you don't really have a name, you only have that pointer, you have to work with that pointer. That means you have to dereference it if you wish to write some data in it. You also have to dereference it if you wish to read some data from it. And what do we forgot here? Okay, we need to delete, of course. So we have a leak here if we just have that piece of code, but how do we fix? We just have delete, and then we give it the pointer, and then the operating system will clean up that heap memory, and it can be used for something else. If you have longer main functions, or anyhow, if you have longer functions, or if you pass that pointer that you obtained by operator new here, if you pass it through across functions, you can do that. You can allocate a chunk of memory within one function, and then the pointer to that memory chunk you can pass around in your program, of course. Maybe you call a different function, you give it that pointer, and then it does some other stuff with it. It can be really hard to see if you have double delete in your program. Sometimes, if you're not very careful, that might happen. And if you have a second delete in here, you will run into the following error. So if you run your program, it will tell you double free or corruption, and then your program just crashes, which is not good. But there's one way out. A good way out is, a professional way out is the following. After you deleted the pointer, the address, you delete using the address of that memory chunk that you just allocated. That's great. And directly after you freed it and deleted and deallocated it, you set the integer pointer to point to the null pointer to indicate, this pointer is now invalid, officially invalid. So you write the null pointer to it. And then if you pass it by accident to another call to delete, nothing bad will happen. Namely, this is because if you call delete on the null pointer, the behavior is well defined and it just has no effect. So nothing bad happens. So after you deleted your memory, set the null pointer to that, assign the null pointer to that pointer, and then if you by accident double delete, it doesn't matter because nothing happens really. Okay, but for most of the time we are smart programmers, so we won't have a double delete, hopefully. So, and now a question, how can we detect such memory issues? The memory issues, for instance, double delete, or you have a leak which you don't free, or you forgot to free. Such memory issues are really hard to find in your program. Pointer analysis is one discipline of static analysis which I work in, so to say. And pointer analysis is an undecidable problem. So it's really hard to figure out statically if your program is correct, because it's a dynamic property of the program, because you really only observe it while running your program. So it's really hard to find such memory issues. But a tool which can make your life somewhat easier is called Valgrind. And Valgrind is a tool to detect memory issues. So you can here go to that link and look it up and read all the details. So Valgrind was developed by Julian Seward, and he is a British compiler construction specialist, so one of the very smart people. And Vagrant is really a tool suite that allows you to detect memory errors. So what it basically does, it runs your program under analysis multiple times, and while running your program, from time to time it stops your program, many times in fact. And then in those breaks, it analyzes the stack, the registers, and it collects all those very important information. And with help of the information that have been collected in the breaks while stopping your program, it can determine whether your program has a problem or not in terms of memory, which is great. But also, please observe that the program under analysis is executed usually 100 times slower than usual. And for large applications, that just needs time. But I mean, it's still worthwhile to make sure your program is without memory issues. So there are not many ways to detect memory issues, as I just told you. Another way which you can use if you're using Clang and the Clang infrastructure and LLVM infrastructure is the so-called Clang address sanitizer, which you can also look up all the details for using that link here. So it's a fast memory error detector, and it's you can use both Vagrant and Clang and see how they perform. And the Clang address sanitizer uses compiler instrumentation and a runtime library, which again also come with some slowdown, so your program only runs twice as fast. But usually you would use that thing, the address sanitizer, to make sure that your program is without any memory issues. And once you proved or checked that, then you would compile your application again without that address sanitizer, and then your program has the usual speed, of course. So this would be one step before you ship your software product usually. And the Clang address sanitizer can detect out of bounds access to heap, stack, or globals, use after free, use after return, use after scope, double free, invalid free, and memory leaks are currently experimental. How do you do it? It's really easy to use the Clang address sanitizer. You just compile your program, which I, in this case here for demonstration purposes, is just one file, myproc.cpp. You have all the warnings, you set the standard, you set some optimizations maybe, you set the -G flag to it tells the compiler, hey, please also include debugging information. And then you use the compiler switch -f sanitize equal address, forcing or telling the compiler, hey, please use the address sanitizer. And also you use -f no omit frame pointer. I won't go into detail why that is important. And then you just compile your program, and then you can run your program. And when your program has memory issues, you will see it on your console output. So it will tell you because of the instrumentation that you turned off using those flags here, essentially. Okay, so what happens here? Maybe let's assume this program from before, and we still forgot to delete here. Maybe we have been unconcentrated while writing that piece of code. And we can now compile that code, and it will work fine, but still it will leak. And if you have a long-running program where you allocate from time to time, eventually you will run out of memory. But if you use it if you call Vagrant on your program, it will tell you, hey, it will analyze your program, and it will tell you, hey, you have definitely lost 4 bytes in one block, and 4 bytes is exactly this integer. An integer on most modern machines is 4 bytes. So it will tell you that you leaked some memory, and also it will tell you in which line, which function here, and it was in main function in line 6. And if you have a delete and everything works fine, it will also tell you, yeah, in use at exit 0 bytes and 0 blocks. And in total, you used 1 alloc and 1 free. 4 bytes have been allocated, but everything is fine. all heap blocks were freed. So that's Valgrind. I don't have examples on the Clang address sanitizer, but you can try for yourself. All right. So that was an individual object, an individual integer. Now we have to see and have to check how it works for arrays. Sometimes you need to allocate arrays. So what you can do is you can use the array new. So here you tell, yeah, please, using the new keyword, the array new, please give me 10 integers. That's the semantics here. So you tell it, yeah, what type, and then the number of the type. So 10 integers. And give me the address of that memory that is allocated, and store the address in a pointer variable array. And then by using this pointer variable array, you can access those 10 integers which are on the heap. And here maybe is a small picture for, yeah, to make up your mind. So this integer pointer variable array, this is an ordinary heap variable. So this, other way around. Once again, so this array is of type integer pointer, and it is an ordinary stack variable. So this array variable resides on the stack. And here by the new int 10, by the allocation of two new 10 integers, you now have 10 integers of the heap, one after the other. So 1, 2, 3, 4, 10 integers. And then you store the address of that chunk of memory consisting of 10 integers and store it in that array variable. So basically how it looks like in memory is you have an integer pointer variable on the stack, and it points to the chunk of memory that you just allocated, which resides on the heap. And also what I told you earlier is do not forget the size. So for instance, if you wish to iterate that chunk of memory here that you allocated, those 10 integers, if you wish to iterate that using a for loop, you need to know how many integers basically you have in that chunk of memory. So here we also have 10. From 0 to 9 is basically 10 integers, this loop. And we can access through this pointer, we can access the individual integers by using the squared brackets operator. And as a shorthand, the squared brackets operator in this case, because this is a pointer variable, is a shorthand. I will tell you what it means exactly in a second. And this iterates basically all integers on the heap, and it writes to each integer, it writes the value 13. Just give me a sec, please. So to each integer on the heap, it writes 13. It basically initializes all integers. And how you could also write it, or how you would actually need to write it, is using pointer arithmetic. Pointer arithmetic is the following thing. You have your variable array, which is a pointer variable, which points to the integer. And so the contents of array is basically an address. And you can also now perform computations with addresses. So you can say, yeah, this address points to the first integer. And just take this address plus I. I is now an integer variable. And you can basically then, if you go around the loop and loop, you iterate through all the addresses here. So if I is 0, you just have array, which is the address to the first integer. And in the second round, if I is 1, it basically means here, go to the next integer stored after this address, which would then be this integer here, the address of this integer. And then by using this pointer arithmetic plus I, and I loops here is the loop index, you basically go through the addresses of the integers. And then the address itself you put in parentheses, and you prefix with the asterisk, which is whatever that address is, give me that content, because this is here the dereferencing asterisk operator. So whatever that address is, dereference it and add 2 to whatever value is stored under this address. And you see, it's a bit complicated. You need to get your head around it. And because this is so commonly used, rather than having to write this second thingy here, you can also just use the squared brackets and it has the same semantics. So this is basically take the address and dereference. Yeah? So same semantics. So always, of course, prefer the squared brackets notation here, because this is hard to read. And at the very end, we call the array delete, because we used array new. And if we call array delete, we can return and we are done. Problem with dynamic arrays here, we need to store the size information ourselves. Yeah, we need to know that 10 integers have been allocated, which is somewhat unfortunate, but you just have to be aware of that. Otherwise, of course, we risk index out of bounds, or undefined behavior, or segmentation fault, or something similar nasty stuff. You can also allocate 2D arrays, aka matrices. It looks a bit different, I would say. I mean, it's the same game basically, but it looks a bit more complex. But maybe let's go through all this. So if you wish to allocate a matrix with 3 rows and 4 columns, how do we do it? First of all, we have a matrix variable which is of type pointer to a pointer of integers, for which we allocate an array of row integer pointers. Oh dear. So how does it look like in memory? So in memory, we have a stack variable matrix of type pointer to integer. And we now let this variable point to whatever this here is on the heap. And we allocate it here by using this nasty expression here. We essentially allocated 3 integer pointers on the heap. So now we have an array of 3 integer pointers, and the matrix variable points to the first of those. Then we continue. So for each row, for each of those 3 integer pointers, we now again in a for loop we call again a heap allocation. So we allocate on the heap integer arrays of size cols. Col is 4 columns, and store it at and store the resulting address, the pointer that we get back from the operator new, in matrix at the position row. So how does that look like? We now have 3 other arrays of integers on the heap, somewhere on the heap, and the first address of each of those integer arrays is now stored in this array of integer pointers. So it would look like the following. Yeah. And now you can iterate the matrix variable to access all the underlying integer. You can double dereference it here. So first of all, you can access the nth row, which would be this one, this one, this one, and then the corresponding column here, which would then be this one, this one, this one, this one, or depending on which row you got the other integer arrays. And you maybe can also initialize everything to 42, because why not? And if you're done with that useful stuff and with your matrix, this is also why you need double pointers sometimes. Now we have to do it the other way around. So now we have to array delete each memory which is pointed to by one of those pointers, basically. So you would get rid of this one, of this one, of this one. And at the very end, you would array delete the matrix to get rid of this array here. And then set it to the null pointer to be sure that we are safe. And then you just have a pointer on the stack and you cleaned up all the heap memory and you're good to go. All right, maybe some more examples, and maybe also let's try to visualize it here so you get a good understanding on what's going on in your computer's memory. So let's have a simple vertex type which comprises 3 double members, x, y, z, and let's give it some constructors. Doesn't really matter. So now what matters is the following, because yeah, different things happen here. If you write that line here, you allocate on the heap a new vertex. A vertex comprises 3 doubles, and that is also why you have 3 doubles allocated on the heap. So you allocate under the hood 3 doubles on the heap, and the pointer to the chunk of memory on the heap you store in a stack variable of type pointer to vertex. So how does it look like? So you have the pointer variable v1 on the stack, it's a stack variable, and you allocated a vertex type, you allocated basically a memory for a vertex on the heap, and this has 3 doubles, which is why you have 3 doubles now on the heap, and you will store the address of that chunk of memory in that variable v1. And by the way, here the default constructor is called. If you do no parentheses, the default constructor would be called, and then all of the member variables x, y, z would be initialized or are initialized to 0. You can also use the other constructor, so you can also use new to allocate another vertex on the heap. So you have yet 3 other variables on the heap, 3 other double variables, which you initialize to 1, 2, and 3, and the address of the chunk of memory you store in the variable on the stack, which goes by the name of v1. Because you really defined here this v2 variable after this v1 variable, it also on the stack comes one after the other. So you first had one pointer variable v1, and now you have a second pointer variable v2, which comes directly in memory next after the v1 thingy. And on the heap, maybe you now get this 3 doubles here, so you have space for 3 doubles, and the resulting the address of the chunk of memory which you allocated is now stored in that v2. What you can also do, and this is what we did before, is you can just allocate on the stack. So you can just really have a vertex v3, which you call the second constructor here, 3 to 1, and initialize all its member variables with 3, 2, and 1. And this thing here, without using new, you just allocate on the stack, which means after those 2 pointers, you now have 3 double variables, which are used to hold, to represent the type, that vertex type, and those are now on the stack. So you, as a programmer in C++, you can decide, should this piece of data go on the heap? Then you use new, or should it go onto the stack? And then you don't use new, you just allocate on the stack here. In languages like Java, you don't have that. For instance, in Java, you always have to use new, and then the virtual machine decides for you whether to put on the heap or the stack. But in C++, again, you have all the freedom. You are in chief. You have to tell what goes where. And you have all the power. When you now wish to access the individual data members of such heap allocated memory, you can use the pointer operator, so to say, so the arrow operator, and access the member variables x, y, and z. And here, for instance, in this case, here we are storing 42 in the member variable x, which would be, let's see, pointer variable v2, we dereference, and then we access x, which is the first double here in the type. So we would basically access this double value here and would write 42 in it. And we can also write v2 to the command line by dereferencing that pointer, and then this left shift operator would be called here. This is very important here. Sorry, I haven't told you that right at the beginning. So, because you have to work with with pointer variables so frequently, and you also have to access members of such pointer variables, you can use the error operator as a shorthand. And the error operand has the the error operator has the following meaning. It basically means dereference the pointer and then access x with the dot operator. So dereference whatever whatever this thing points to. So meaning go to here, and now this dot x is use the member variable x, which would be the first double here, as I pointed out. And because you need that so frequently, and it's a bit painful to write, you can use the error operator here. So this means dereference and access the member variable x. That's the meaning. And now we have to get rid of the heap allocated memory. So we delete v1, which basically frees this 3 doubles here. Those have 3 doubles. And we set it to the null pointer here because we're good programmers. And then we delete v2, which gets rid of those 3 doubles here on the heap. And also we set it to the null pointer. So, dynamic memory allocation. Just give me a second, and then we continue on something, more sophisticated. So, last time I told you copy and move can be defaulted for the simple types, which only use STL data members and built-in data members. But if you have data types which use dynamically allocated heap memory, we have to define copy and move, the copy and move special member functions ourselves. And we will now, on the next few slides, have an example on how that works and how you would do it for a simple type. And on the current exercise sheet, you have to do it yourself for another type, for a type that manages a dynamically allocated array. And here in this lecture, we will have it for just a dynamically allocated object and not an array. All right, let's see how it works out. So maybe let's play the naive game. So let's play the stupid guy, and let's just do it as we did it before, and let's see what happens, and then we start and fix our way from there. All right, so the type that we are using is a dynamic integer. So we now write ourselves a new type. We implement a new type using the struct keyword, so everything is public, and we call the type dynamic integer. And that dynamic integer has as a data member a pointer to an integer. And dynamic int is a type which we desire or demand to manage a heap allocated, so a dynamically allocated integer. So this dynamic integer type should manage dynamically allocated integer type. That's why we have a pointer as a member. We also have a standard constructor or a constructor which takes an integer value and we initialize this member variable, this pointer to an integer. We initialize that with the following expression here. So new int, so we allocate an integer on the heap and initialize that heap allocated integer with whatever the user provides as an argument to the constructor. So we use the value provided by the user to initialize our heap allocated integer variable, piece of memory. And the address to that heap allocated memory we store in the variable iptr, which is a pointer variable, so it's perfectly fine. And we also have to do the cleanup, and of course it makes sense to just use the destructor. So in the destructor we just delete whatever this pointer variable points to. so we can't forget. So this is why we use the destructor. So that's good news so far. Let's also have ourselves the output stream operator overloaded such that we can print the contents of the value that is stored in the heap memory pointed to by IPTR. So sometimes it's really hard to even tell what's going on and what you mean, but that's the purpose. And now let's play the naive game and let's just default the copy constructor. All right, and let's also default the copy assignment operator. So, and now we can write ourselves the following piece of code. We create a variable di1 of type dynamic int, and we use the constructor which under the hood allocates a piece of heap memory, an integer on the heap. It initializes that with 42, and the resulting address is stored and maintained in that member here, in this pointer member variable. And now let's call for the, that's wrong actually, this would be the copy constructor. Sorry, this is not the copy assignment operator, it's the copy constructor, call to the copy constructor. All right. And what happens here is because we use the default copy constructor here. In the last lecture, I told you if you set the copy constructor to default, it performs a member-wise copy of that thing, because that's best that the compiler can do on its own. So that means the di2 variable is now created as an exact copy of that thing. That also includes the pointer variable that d1 contains. Now also d2 has the IPTR pointer variable points to the same heap allocation. And if we now write the value of 100 to that IPTR of d2, we changed it in the heap, so the change is also now visible in the di1 variable, because as we just performed a naive member-wise copy, both pointers of di1 and di2 point to the same location in heap memory. And if you do a change to that heap memory, this change is visible to both types, both variables, di1 and di2. And here with my fingers, that's the best I can do without a chalkboard, unfortunately. And now here we have even more oops. So now we call the destructors for di1 and di2. And in the destructor, please recall that we call delete. And this also means, because we have a member-wise copy, so di1 and di2 are member-wise copies from each other, we now call delete twice on this pointer. On the same address, we call delete twice, and I told you that you shouldn't do that, and that means we have a double free and a memory corruption. So this is what you get if you then call that program. So it doesn't look any good. So how would you fix it? Now we need to fix it really, and we just saw that just performing a member-wise copy is not sufficient really. So we have to perform something which is called a deep copy. So we not only need to copy the members, but if a member is a pointer which points to dynamically allocated heap memory, we also have to copy that heap memory, and not only the stack members, so to say. So this same game as before, so same constructor, same destructor, same output stream operator. But now we create a deep copy, not only a shallow copy of each data member, but a real copy. So the copy constructor now needs to implement how we copy, and or source basically from which we need to copy is the variable di, which is provided here as a const ref. So we shall now create something which is an exact copy of di, of the di variable. And okay, what do we do? Now we need a deep copy. That means we also need a piece of heap memory, which is why we initialize the iptr member in the copy constructor with a new allocated integer. So we also now in the copy constructor allocate something from the heap, namely a new integer. And this integer we initialize with the value of the iptr variable of the di variable we wish to copy from, really. And we dereference that to get its integer value, and we use that integer value of di to initialize our own new heap allocated memory. And now we have a deep copy. We did not just naively copy the member, but we did we also did the heap allocation and also copied the memory from the heap. And this should now all work fine. This can be left as default, because if we have a copy constructor working, then the copy assignment operator most of the time works also fine. All right, that was copy. Now let's talk about move. So we know how to do the copy, and now let's also play the naive game on the move constructor. Oopsie. And let's just set it to default and see how bad it gets, and also the move assignment operator. So similar story here. So we create a variable of type dynamic int by the name of di1, and we initialize this to 42, which under the hood allocates an integer on the heap, initializes it with 42, and stores the address of that allocated heap memory in the member variable iptr. So far so good. We now call the move constructor, and also, sorry, that's not true, that is the move constructor in this case, by using std move here. So we move from that di1 and we construct di2. And now does it work? If we just try to set the value of the allocated heap integer using this expression here, this should still work fine. But if we run that program, we still get a double free, because move by default also only performs a member-wise copy, because it doesn't know better, so it performs a member-wise copy. But as we handle here with heap memory, a member-wise copy is not sufficient, because the error is basically the same here. We have now two variables, di1 and di2, whose member variable iptr points to the same heap location, which we then in both of the destructors delete twice. And this is prohibited. This is a double free corruption. And this is why our program crashes. So how do we fix that? I told you that the move constructor basically steals the memory it should move from. So from whatever we should move, we just steal the memory. Let's see how it works. So the variable we shall steal from, that we shall move from to construct our own variable, is di, the parameter of the move constructor here. And what we now do is we just steal its data. We steal di's data in order to construct a new dynamic integer. So how do we do that? How do we steal data? We now set the iptr data member of the dynamic integer to be constructed to the iptr, to whatever this pointer points to from the di we shall move from. So read the IPTR pointer from the di variable and store it into our own IPTR pointer that we shall basically construct an instance of. And so we basically have the pointer of the move constructed variable also pointed to the same heap allocation. So now in computer memory we have now two pointers pointing to the same memory. So we construct the move constructed di2 variable by first of all here performing this statement, which also has the other pointer pointed to the same heap memory. So that's not too good, because we I think of what we observed on the last few slides. But now comes the catch here. The PTR, after we copied the address here of the di variable we should steal from, we now go on and set the IPTR pointer member of the di variable we just stole the data from. We set it to the null pointer, which just gets rid of the second pointer to the heap memory. It just removes the second pointer to the heap memory, and now we only have one pointer to that heap memory. So we construct a variable di1 here. The heap allocation takes place and the heap memory is initialized to 42. Now we move construct a di2 variable by stealing the heap memory of di1 and setting di1's pointer to that heap memory to the null pointer. And then we can do some stuff with that, and at the very end the destructors are called. And so the destructor for the di2 is called, and it works perfectly fine because we have one pointer to that heap memory, everything fine. And then the destructor for the di1 is called, for the destructor for the di1 variable is called, which deletes whatever IPTR points to. But as we in the move constructor set it to the null pointer, nothing bad happens. So it's perfectly fine, perfectly legal, nothing bad happens, and we solve the problem here. And for most cases we can also now set the move assignment operator to default, and it will work most of the times, in quotation marks. So that was hard, but really you can also take the example from the last few slides and really have a piece of paper and a pen and really draw what happens under the hood. You can draw some segments of stack and heap memory, and then you can also draw where what piece of data is and what points to what, and what happens if what special member function is called. So you can also go through it one by one, little by little, on a piece of paper, which also makes it much more understandable. But now you can really relax, so you now know how to handle special member functions in the context of dynamic memory allocation, and it will not get any more complicated than that. If you manage to swallow that, if you have a clear mind of how it works, then you are now pretty much unstoppable in terms of your C++ programming skills. So probably like this guy here. So at last we are almost finished. Just a few notes which may be very useful to you. So first of all, a note on special member functions using built-in and STL types. So STL types provide many useful constructors, and STL types also know how they have to be destructed, copied, moved, and copy assigned and moved assigned, because they all define those special member functions. That means if you are dealing with types, if you write yourself an own data type which only contains built-in primitive types, so like int, double, and all that, and STL data types which implement all their corresponding special member functions, then default works perfectly fine. But if you're dealing with the dynamic memory yourself, like we did on the dynamic int data type or on the vec data type that you're going to implement yourself in the exercise classes, you need to know how to deal with those special member functions, especially copy and move. So notes on dynamic memory allocation. So we just use draw and delete directly. but raw, new, and delete rarely need to be used directly anymore. They're in fact too error prone. Usually there's also no need for raw, new, and delete because there are alternatives, which I mention in a second. However, there are of course exceptions. So sometimes there are just places where you need to call new and delete, and you have to be smart about it in order to don't run into any trouble or issues with your program. There are exceptions, but for most application programs, you are perfectly fine not using raw, new, and delete. So what should you use? If you need to allocate just one object, just use the stack memory. Just allocate it on the stack if it's not too big, too large to fit on the stack. Also, please maybe note that I haven't mentioned that yet, but I should probably do. Allocations of different kinds of memory has different performance. So the fastest memory that you can allocate is stack memory, because I mean you have something which is called a stack pointer if you are familiar with computer science and already heard Algorithms and Data Structures 1 lecture. So a typical CS1 lecture covers that, hopefully. So if you need to allocate on the stack, which we usually do if we don't use new, you allocate by just increasing the stack pointer, which is basically one command, and then you have space on the stack. And allocating on the stack is fast, is really, really fast. Whereas if you allocate on the heap using new, it's a bit more expensive, because you actually have to call, you have to ask your operating system's kernel, which runs your program and runs all the operating stuff, to give you memory. Then it has to check, do I have some memory available still, and then it gives it to you, and it takes more time. So if you use new, it's usually more expensive. It's not that expensive that you can't use it, but keep that in mind that stack allocation is the fastest allocation, kind of allocation that you can perform. So if you need to allocate one object, just do so using stack memory and just return by value, and the return value optimization and move takes care of performance. You can also use move if you wish to move variables between scopes. So if you need a variable that needs to live longer than one scope, you can just, here's an example, we have an outer scope variable int and we have an inner scope variable int of type int. Initialize it to 42, and then we set the outer scope variable and we move the variable from the inner scope in the outer scope. And here you could just also have performed a copy because it's a simple int data type. But if it would not be int but a more complex data type, then move takes care of performance, and it move constructs the outer thingy here. And move construction is usually pretty fast because you steal the data and do not allocate yourself, you just steal from something else. All right. If the object is too large for the stack, then you can use dynamic memory allocation. Then you can use new, and then the lifetime of that object is under your control. So if you, how about arrays? If you need to allocate a fixed size array of objects, so an array which is statically fixed at compile time, also, first of all, just use stack memory. So you can just use an ordinary array, maybe an integer array of 10 ints, which you can declare and define here as follows. If you use C++11 and above, which you hopefully use, you can also use the safer wrapper type in the STL. The STL provides a stud array implementation, and stud array is a safe wrapper around a built-in array, which you can also say, hey, this should be an integer array of 10 integers, and you give it the variable's name or data. And this stud array type also knows its size, whereas in the former built-in array, you have to carry the size of 10 yourself somehow. So always prefer the stud array wrapper type if you need to allocate a fixed size array on the stack. if you need to dynamically allocate an array of objects, because maybe you don't know the number of objects you need up front, then rather than using a new array new operator, just use the std vector type. So the std vector type implemented in the STL is a safe wrapper around a heap allocated array. So it was created exactly for that purpose, and it acts as a safe wrapper for dynamically allocated arrays. So it can also grow and shrink in size. It also carries the size information. It provides all useful operators, implements all useful operators. It implements all some more useful member functionalities, which you can just use out of the box. And this will be one of the exercises of the current exercise sheet to basically mimic std vector data type. So you now need to implement your own vector type, which stores elements in a heap allocated array. That's basically exercise 1 of the current exercise sheet. So you get a good feeling how it works under the hood. So if you need raw, new, and delete, nevertheless, then try to use smart pointers rather than raw pointers, because remember about the delete issue. So if you forget delete, you leak memory, and if you double delete, you have a double free and you corrupt your memory, and then everything, all hell breaks loose, so to say. So use smart pointers. Smart pointers take care of the deallocation themselves. Smart pointers themselves know when to do the cleanup, when to delete the memory. And this really means that you can't leak memory anymore if you use smart pointers and follow some rules. Also, this is called the poor man's garbage collector, because it's no real garbage collector, but it's implemented under the hood by something which is called reference counting. So we will discuss about smart pointers in one of the next lectures, and how a smart pointer works. To give you a quick hint is it manages some piece of memory allocated on the heap, and it has the pointer to that heap memory, and also it stores the number of users of that piece of memory. And if the number of users can increase, of course, but at some point the number of users also decrease. And if the number of users hit 0, then the deallocation, the call to delete takes place, and it is safely cleaned up. So this is called reference counting. We will go into all the details in the corresponding lecture. So recap, operator overloading. We discussed about operating overloading, programs memory layout, dynamic memory allocation for arrays, for objects, and array new, array delete, and ordinary new and ordinary delete, and please don't mix them up. We also talked about Valgrind and the Clang address sanitizer, and there are also more sanitizers that Clang provides, so please just go to Google and go for Clang sanitizers, and then you can find all kinds of useful sanitizers that you can apply to your program to improve on your program. We talked about copy and move constructor in the context of dynamic memory allocation, and at the very end some notes and hints on dynamic memory allocation, so when to use what. And that is pretty much it for today. So thank you very much. If you have any questions, which might well be the case, use the forum on Panda. Otherwise, I will see you sometime this afternoon during the live stream. And other than that, have a nice weekend and see you next week. Bye bye.